So which phenomenon is described by the underlined words, right? The light ray changes direction every time it passes into a new medium. The light ray changes direction every time it passes into a new medium. We know fully well that is refraction. A light ray changes direction every time it passes through a new medium. And then 7.2 says, if the refractive index of water and air is 1.33 and 1 respectively. So what does respectively mean? For water, the refractive index is 1.33, and then for air, the refractive index is 1. So let's denote that in our sketch, right? For air, the refractive index is 1, and then for water, it's 1.33. Calculate the angle theta between the light ray and the surface of the water. So we want the angle between the light ray and the surface of the water. If the angle of refraction in the water is 40 degrees, the angle of refraction is 40 degrees. So fine, let's write our information down, right? So N incident, where is our light ray incident? It's incident on the air, right? And then the refractive index is 1. And then N refracted, the medium the light ray is moving into. We know that that is water, right? And the refractive index is 1.33. And then we are given the refracted angle. So theta R for refracted, which is said to be 40 degrees. And then the question is saying, let's find the angle of incidence of the ray, right? So that's what we're looking for. It should be easy to see that we're going to use Snell's law, right? Which says that Ni sine theta of I is equals to Nr and sine theta of R. You can use N1 sine 1 is equals to N2 sine 2, whatever you're comfortable with, right? So what is the refractive index of the first medium? That is 1, right? We're coming from A. And then what is the angle? That's exactly what we're looking for. And then the refractive index of the medium we're moving into, that is water. The refractive index is 1.33. And then sine of theta, right? We're given the angle of the refractive ray relative to the normal. It is said to be 40 degrees. So now we can divide both sides by 1, right? When you divide both sides by 1, we're still gonna get whatever we have. So now we can basically say that theta, or the angle of incidence, will be equals to sine arc of 1.33 multiplied by sine of 40 degrees. And then if you put that in your calculator, you're gonna get 58.75 degrees. So what are we saying? Let's come to our sketch, right? This is the normal. We're saying that this angle here is 58.75, right? And then if we keep our normal going, this angle here, we are told that it is 40 degrees. Let's use 7.3. 7.3 is saying that the angle of refraction in the glass is 35 degrees. Calculate the refractive index of glass. So again, physics 101, right? We start by writing down the given information. So this angle of refraction from air to water will be the angle of incidence from water to glass, right? So now we know that the angle of incidence is equals to 40 degrees. And then we are given the angle of refraction, right? So the angle of refraction is equals to 35 degrees. What else do we know? We know the refractive index of water, right? We know that Ni is equals to 1.33. What we're looking for is Nr, which is our x, right? So again, if you apply Snell's law, we're gonna get Ni sine theta of I is equals to Nr sine theta of R. So what is Ni? we're coming from water, right? So it's 1.33. And then the angle is the angle of refraction from air to water, right? That is sine of 40 degrees. That will be equals to NR, which is what we're looking for. And then the angle of refraction from water to glass is given to us as 35 degrees, right? So now we're going to say 1.33 multiplied by sine of 40 degrees divided by sine of 35 degrees is equals to NR multiplied by sine of 35 degrees divided by sine of 35 degrees. We're solving for NR, right? And then if you put this in your calculator, you're gonna get 1.49 is equals to NR, right? So the refractive index of glass is 1.49, and then it makes total sense. We would like to think that the refractive index of water is greater than that of air, and the refractive index of glass is greater than that of water, right? Let's move to 7.4. So 7.4 is saying draw the sketch below and complete the diagram of the path of the light ray from the air to the water to the glass. Show all the values of the angles of incidence, angles of refraction, and the normal in each medium. So let's just do that real quick, right? So we calculated the angle of incidence on the air, right? The angle of incidence on the air is not this theta here, right? We calculate the angle of incidence relative to the normal that I'm just constructing right now, right? We said that that angle is 58.75 degrees, right? And then that ray, it gets refracted when we move from air to water, right? And there goes our ray, right? Now we can construct our angle of refraction, right? The angle of refraction, it is given to us as 40 degrees. But then this angle of refraction from air to water will be our angle of incidence from water to glass, right? So if we construct a normal here, we should have an angle of 40 degrees from water to glass. And then again, when we move from water to glass, the ray will get refracted, right? The ray is getting refracted, and then now let's construct our normal and place our angle, right? The angle of refraction is between the ray and the normal and is given to us as 35 degrees. If we're moving to a new medium, then this angle of refraction will be the angle of incidence from the glass to the new medium. Now we can do 7.5. 7.5 is saying calculate the speed of light through the glass prism if the refractive index of glass is 1.5. We are given the refractive index of glass, it is said to be 1.5. But we know fully well that the refractive index is equals to the speed of light in vacuum divided by the speed of light in the medium of interest, right? Here we want the speed of light through the glass, right? So what is the refractive index? We know that that is 1.5. And then what is speed of light in vacuum? 3 times 10 to the 8 meters per second, right? Divided by the speed of light in the medium. So right now we're cross multiplying and dividing both sides by 1.5, right? We're gonna get the speed of light in the glass prism being equals to 3 times 10 to the 8 meters per second divided by 1.5. And then if you put that in your calculator, you're gonna get 2 times 10 to the 8 meters per second. 7.6 says that, is it possible that total internal reflection of the light ray can occur in the above situation, right? Only yes or no, right? So first thing first, what is total internal reflection? Total internal reflection is when a light ray gets inside a medium, right? And then it doesn't leave the medium. Let me show you a demonstration. So let's say this is our medium, right? And then we have a light ray coming in. If this light ray comes in and the angle of refraction is either 90 degrees or greater than, then the light ray won't leave that medium, right? If it's 90 degrees, then you can see that the light ray stays in the medium. And then if it is greater than 90 degrees, then the light ray actually gets reflected, right? And then you can see here in our diagram that we don't have any angle of refraction which is 90 degrees or greater than, right? Since we don't have that, no total internal reflection will occur.